In this video, we're going to evaluate the following integral. Integral of x squared minus x plus 6 over x cubed plus 3x dx. To evaluate this integral, we're going to apply the method of partial fractions. But let's first check if all conditions are met so we can start that method. So first of all, we can see that we have a rational function here. Numerator is the polynomial, denominator is the polynomial. Second, I have to check if I have any common factors in the numerator and denominator. I'm going to rewrite my function here. Now, the denominator I want to be in factored form anyway. So x cubed plus 3x. I can factor it by factoring out the common factor x. So it's x times x squared plus 3, right? Okay, now the numerator, I don't need to have in factored form, but even if I try to factor it, I wouldn't be able to, so it's not factorable, and I'll just rewrite it. But this confirms that there are no common factors for the numerator and denominator. That's good. If we find common factors, we have to divide them out. Simplify expression this way. Next, we need to confirm that degree of the numerator is less than degree of the denominator. It's convenient to do over here to check that. So degree of the numerator is 2, degree of the denominator is 3. So yes, it's a proper rational expression. And now let's observe what kind of factors in the denominator we have. So here we have two factors, x and x squared plus 3. Well, obviously x squared plus 3 is quadratic factor, right? And it's also irreducible. It's irreducible because it's a binomial and it has plus sign. So whenever you have quadratic binomial with a plus sign, it's going to be irreducible. Okay, but then what is the first factor? Well, the first factor is actually a linear factor. If you don't recognize it, maybe I can write like that, x plus 0, right? Now it looks a little bit more the standard form of a linear factor, right? But I'll keep it as x, so I only need to know that's a linear factor. We're ready to start partial fraction decomposition. We're going to do it on the side. It's going to be our scratch work on the side, and then once we decompose, then we'll continue with the integral. So I'm going to rewrite my rational expression over here. Now I can split it up into separate fractions, into partial fractions. I have to remember that every factor of the denominator is going to have its own fraction. So x is going to have its own fraction plus, and then x squared plus 3 is going to have its own fraction. I also need to observe that each factor is repeated only once. X is repeated only once since I don't have a power. And then x squared plus 3 is only repeated once, right? And because of that, it's only one partial fraction for each factor. Next, we need to write down the numerators, right? At this point, I want to remind myself one more time that this denominator is linear and this denominator is quadratic. So every time I have a linear denominator, the numerator will always be just a constant. I'm going to use a for that constant. But every time I have a quadratic denominator, its numerator is going to be linear expression. So it's going to have this form, bx plus c. I have to keep using new letters every time, so that's why if I used a, now I'm moving on to b and c and so on and so forth if I add more fractions. But that's all I have here, right? A is here because it's linear, and then bx plus c is over here since it's quadratic. So that's the idea. So we split it, right? We split it up, but our goal is to find a, b, and c. So to do that, once we split, step 1, then we're going to combine them again. Now to combine them, they have to have same denominator, and that means that I have to, which is the LCD will be just the product of those two, right? It means that I will need to multiply each fraction by the missing factor. So the first one is missing x squared plus 3. And I have to multiply on the top and on the bottom. And the second one is missing x. So times x times x. Now I'm going to write what I have. Now the denominator is combined and it's x times x squared plus 3. I'm going back to that denominator, right? Numerator is a times x squared plus 3 plus bx plus c times x, right? So those two. Now I'm going to simplify the numerator. So the numerator is I'm going to simplify by distributing a and by distributing x. So I'm distributing a and I'm distributing x. Let's see. It's ax squared plus 3a plus bx squared plus cx, right? And here's the denominator. Now there's no point of dragging that denominator from step to step anymore, because this is what I'm going to write now. So idea here in order to find a, b, and c, I need to realize that my original numerator is the same as my resulting numerator, and I'll force them to be equal. So I'm going to write down the numerators. So numerators. X squared minus x plus 6, that's the original. And now I'm going to write down the resulting numerator. The only thing that I have to rewrite it, because this is what my next goal is going to be. Next goal is to compare and set equal all the coefficients of the original numerator, all the constants from the original numerator, with all the constants of the the resulting numerator, right? Because they are equal. So in other words, coefficient of x squared, I have to set equal to the coefficient of x squared on the right hand side. Coefficient of x, I have to set equal to the coefficient of x on the right hand side, and so on and so forth. And the constant is going to be equal to the constant. So I just need to make this more obvious for me. What is the coefficient of x squared? I have two terms with x squared, so I'm going to combine them or put them together, and I'll factor out x squared. So if I pull out x squared, then I'll have a plus b left. So in other words, it's a plus b x squared, right? Then I need to obtain all or find all terms with x. I only have one here, so it's plus cx. I'll just write it. Rewrite it, and then only one constant, right? So constants are all going to be all letters with no x's present. So I only have 3a plus 3a. And now as I organize the right hand side this way, now I can clearly see where the coefficients of x squared, x, and what is the constant. And I'm going to set them equal. So coefficient of x squared, I'm going to set equal to coefficient of x squared on the other side, so set equal. Next, I'm going to take coefficient of x, and I'm going to set it equal with the coefficient of x on the right hand side. And then finally, I'm going to take the constant, and I'll set constant on the left hand side, and I'll set it equal to the constant on the right hand side. And here's the system that I'm going to obtain. A plus b equals, now what is the coefficient here? It's 1. A plus b equals 1. Then coefficient of x here is just c, so it's going to be a pretty easy system to solve in this case, equals the coefficient of x on the left hand side, so it's negative 1. And then the constant 3a equals constant on the left, that's 6. Now in this case, we got system that's very easy to solve because we already have two answers here, right? So c equals negative 1. From 3a equals 6, a will be equal, I need to divide by 3 on each side, so a equals 2. A equals 2. And knowing a, I can always find b. So if a is 2, I'll continue. So from here, 2 plus b equals 1. That means that b equals, I subtract 2 from each side, b equals negative 1. So we found a, b, and c. Now a lot of times you'll have to do a few more steps here to solve the system, but just use either elimination method or substitution method. to find those constants, those values of a, b, and c, and so on and so forth. Okay, let's put this all together. So this is what we have. We started with the expression x squared minus x plus 6 over x times x squared plus 3. And this is how we decomposed it. So decomposition shown over here. So it's a over x. Now what is a? A is 2. So it's going to be 2 over x plus bx plus c over x squared plus 3. So plus bx plus c. So that's negative 1x minus 1 over x squared plus 3. And over here, I think it's going to be easier if we factor out negative 1. So if I pull out negative sign, it's going to be just x plus 1. And that negative sign I can place right here. So that's 2 plus x minus x plus 1 over x squared plus 3. Like that. And once you decompose, once you create partial fractions, then you're ready to integrate. Let's try to integrate. I'm going to start a new page. Okay, so I copied everything down. That's our original integral, the way it was given to us. That's when we factored the denominator, and now that is the partial fractions, right? In other words, from one rational expression, a pretty complicated rational expression that we couldn't integrate right away, we went to the difference of two simpler rational expressions that now we can try to tackle. And it's always good to work on one thing at a time and then put it all together, right? Because we have a difference, so we can integrate each term. So I'm going to put integral 1 and integral 2. So, and I'll work on the first one. So the first one is integral of 2 over x dx, right? Well, the constant 2 I can put in the front, and then I will recognize what I have here. So that is just a ln, right? A ln function. So it's 2 ln of absolute value of x. I'll put plus c at the very end. Okay, so first one c was very easy. How about the second integral? The second integral. It's integral of x plus 1 over x squared plus 3 dx. So how do we approach the second integral, or second part? Now, I just want to make a disclaimer that generally integrals like that, the whole process will be time consuming, so just kind of accept the fact, accept the reality that if it's taking you too long to complete it, well, that means that you are on the right track. These are not the examples you're going to do quick and easy in 1 minute. So now, how do we approach this? Well, we probably have to split this integral into two more. And we're going to do that by... so I real quick thought about doing U substitution here, or basic substitution rule, and it's not that convenient, even though, you can try that. I think it would be good to split it like that. So remember, rational expressions can be split over the numerator. So it means that if we have sum or difference in the numerator, we can split like that. So it's integral of x over x squared plus 3 dx plus 1 over x squared plus 3 dx. So be careful, because you cannot do that over the denominator. Denominator cannot be split up, only the numerator like that. And that means that I have like two more pieces here. I'm going to call it piece 2.1 and piece 2.2. Okay, working on 2.1. 2.1 is, since I have x and then x squared plus 3, I think we can just apply basic substitution rule here, right? What if that expression is u? So what if u is x squared plus 3? Well, then du is going to be 2x dx, right? And I do have x dx. See how I have dx, x dx, so that works out nicely. Now from here, 1/2 du equals x dx, right? So it means that I'll have to replace it by 1/2 du. Okay, so that gives me integral of, I'm going to put 1/2 in the front, integral of 1 over u du, right? And that is 1/2 of ln of absolute value of u, which is 1/2 of ln of the absolute value u is x squared plus 3. X squared plus 3. By the way, it's something positive, so right, that's always positive. That expression is never negative. So that means that we can just drop the absolute value. X squared plus 3, like that. Okay, so that's our answer for 2-1. Okay, that was number 1. Now we only have, I just underlined that. Got 2 pieces, the third one, 2.2. 2.2 is integral of 1 over x squared plus 3 dx. Now, when I look at this integral, I realize that I cannot do the basic substitution rule here, right? Integration by parts would not work. Things would get only more and more complicated with that. But based on what I have in the denominator, or based on the structure of the denominator, I can see that I have x squared plus a number. So that could work for trig substitution, right? Because that could follow, if I do correct substitution, like a smart substitution, that could follow a pattern or a formula from trigonometry. So let's think. What should I replace x with so that it works the way I want it to work? So that formula from trig, it has to have pattern function, trig function squared plus a number. Well, that's the one that comes for tangent, right? So tangent squared plus 1. That's the one, or 1 plus tangent squared. I don't have 1. I need to grade 1. I need to get rid of 3. So I would need to factor it out. That's how we usually get rid of the not wanted number and create 1. But in order for me to factor out 3, I have to have 3 over here. So long story short, I will be using tangent of theta, but once I plug that, and something else, once I plug that all into here for x, I have to end up with 3 tangent squared. Well, if I want to end up with 3 tangent squared after I square, it means that I have to start with square root of 3 tangent theta, right? So x is square root of 3 tangent of theta. Once I square that, I'll get 3 tangent squared of theta, and I will be able to factor out 3. Let's write down how we're going to replace dx, or what we're going to replace dx with. For that, I have to find derivative of tangent. So derivative of tangent is secant squared, and constant stays. Square root of 3 secant square root of theta d theta. Okay, that's dx. Square root of 3 secant square root of theta d theta. Okay, so let's put this all together. Integral. I'll put this in the numerator. So square root of 3 secant square root of theta d theta over, in the denominator I have square root of 3 tangent of theta squared, that's x squared, plus 3. Okay, what's that? Now, square root of 3 I can put in the front for now. Secant square root of theta d theta. In the denominator I have, maybe I'll write something here so I can save space. That's, if I square, it's going to be 3 tangent square root of theta plus 3, right? But then from here I can factor out 3. Tangent square root of theta plus 1, right? Maybe I can even go further with simplification here. Now, what is tangent squared of theta plus 1? That is same as secant squared, right? That's same as secant squared of theta. So long story short, I have 3 secant squared of theta. That 3 I can put in the front, but since it all sits in the denominator, that number will be in the denominator. So it's like that, square root of 3 over 3. And then secant squared of theta gets in the denominator. Okay? And things are turning out pretty nicely here because I can see how secant squared and secant squared can be cancelled. So I only have square root of 3 over 3 integral of 1 d theta. And that is very easy to integrate, right? So we get square root of 3 over 3 theta. Well, almost there. The last thing we have to do is to replace theta with original variable, which is x. And we're going to get that from our substitution. Since it's just theta, it's not a trig function, but just theta, it means that I have to obtain theta right from here. First, I'll need to rewrite tangent theta by itself. So it means that I will be dividing by square root of 3 on each side. So it's x over square root of 3 equals tangent theta. And then from here to solve for theta, I just need to use inverse tangent function. So theta equals tangent inverse, so kind of theta and then x with the number switch places. Theta sits outside now, and then tangent inverse of x over square root of 3. Like that. So that's what theta is. So that's square root of 3 over 3 tangent inverse of x over square root of 3. And that's the last piece here. The only thing that bugs me right now that we have square root of 3 in the denominator. So I would want to rationalize that. So let me just rewrite it. I would need to I need to multiply by square root of 3 on the top and on the bottom. So I'll have here, let's say x square root of 3 over 3, like that. So that wouldn't have any radicals in the denominator. Well, that's our third piece. Now it's just putting this all together. I'll rewrite our original integral, x squared minus x plus 6 over x cubed plus 3x. And I will put together all the pieces. I need to be careful because I had the minus sign. So as I go back in front of that second piece, that I split it into 2 more pieces later, right? 2.2, 2.1, 2.2, those two. I had minus, so it means that I will have minus in front of each result. So I'll start with 1. That is 2 ln of absolute value of x. That's the first answer. And then minus 2.1. In 2.1 I got, right here, I got negative, so minus 1/2 ln of x squared plus 3. And then minus, so that minus had to be distributed, minus my third piece, square root of 3 over 3 tangent inverse of x square root of 3 over 3, like that. Now again, it seems like too much just because there are a lot of parts in this problem, in this integral. So first you want to start by creating correct partial fractions, and I didn't mention that, but it's also something that's important. Let me find my paper. I went back to the place where we created partial fractions. What's very important is to check your answer here, because if your answer is incorrect, if you accidentally miscalculated something, even if it's a sign, then the rest of the solution will be wrong, right? So when you're here, double check if you decomposed fractions correctly. So combine those two expressions, and I can see here, I can do them in my head. So I can see that, yeah, I'm getting back to my original numerator, so make sure that you got it right. And then after that, well, knowing and seeing how to integrate each, it's a different story. So that's where you have to use your skills for integration, skills different from integration by partial fractions. So your previous knowledge. But yeah, that's how you would approach this example. So it has a lot. So think about it as like one part, one step at a time.